Cool. Okay, so last class, what did we talk about? What did we talk about? Yeah. Yeah, we talked about ripple carry adders. What were some like thoughts that we had about ripple carry adders? So like, what is a ripple carry adder? Yeah.
It's like connecting the adders in series, but because they're in series, they take extra time to do that.
Exactly, yeah. So it's when you have a bunch of full adders all connected in series that all kind of rely on one another. And so because they're in series, it actually takes a while for all of the data to propagate. So this is actually kind of a slow design, but it's okay. Good enough teaching example. Just kind of get your brain thinking for future classes where potentially you'll learn more advanced adders. Okay, cool. We also talked more about delay, right? Yeah. So the idea that when your inputs switch, you will have different, like, varying times of when it will arrive at the final output. And so some switching conditions will propagate very quickly. Some switching conditions will propagate slower. Yeah. Okay, cool. I want to show you something kind of cool. So now that we have engineered this adder circuit, and we could probably imagine it'd be pretty easy to just make it like bigger, right? We could probably just put on some more full adders. So we probably know how to make like an n-bit adder circuit. Yeah, like a 2-input n-bit adder. Okay, so in general now, that means that we don't need to draw out this big circuit. And anytime I ask for you to, like, whatever, design a circuit, and you're like, oh, I need an adder in this, now you can use this adder as a black box. And you don't necessarily need to show exactly what the implementation is. Now you can just say, oh, okay, so assume it has these inputs, assume it has these outputs, and assume that the functionality was implemented correctly. So now you have access to this black box. So I'll just call this an n-bit 2-input adder. Great. This is our first black box in the class. Hope you're all excited. There's going to be many more throughout the quarter. Okay. In fact, we're going to learn one more right now. So a very common circuit is like, yeah, okay, so assume we have this adder, and maybe we want to like check if the sum is equal to something. Okay, so very, very kind of common circuit is like an equals operator. So I don't know, yeah, maybe we want to say like, if we want to check, given two numbers, is their sum 5? Okay, so so if we have inputs A and B, and you know what? Let's use a bus notation. So a bus notation is when you have a slash through your line. So let's say these are 7-bit numbers. Sorry, let's make them 8-bit numbers actually. And so that means that just above this slash we can say 8. And now we can access any one of these bits by saying like A0, A1, A2, A3, A4, A5, A6, A7. So that's all 8 possible indices of this bus. So here are our buses. Okay, so if we want to check if their sum is equal to something, what's probably the first kind of logic cell that we want to instantiate here in our schematic?
An adder?
Yeah, exactly, an adder. Perfect. Yeah, because we want to check their sum. Okay, so if we have this adder now, we can just add a plus sign. Okay, boom, we have an 8-bit adder. That's all we need. Okay, and then now we take this and we want to check, if this sum is equal to 5. Oh, actually, another quite small thing. So what is the bit width of this wire right here? Is this just like a 1-bit wire, or is this a bus? Yeah, and how many bits is it? Yeah, so it's either 9 or 8, depending on, I guess, what functionality you want. If it was a 2's complement, adder, how many bits would it need to be?
9.
Yeah, it would be 8 bits if it was 2's complement in order to correctly round and cut off for like negative values. Let's assume this is like an unsigned adder, so we can just say it's 9. Okay. Okay, so now I have this, and now this comes out, and then maybe we can just feed this directly into like an equals 5 unit. So equals 5. Maybe this is our output. And what is the width of this wire right here? Yeah, it's probably just 1. It's just like, does it equal 5 or does it not equal 5? Yeah. So if we want, we could specify like a bus width of 1, or we could just leave this off. I'll leave it on for now. Okay, cool. And then this is our output. Maybe this is our output Y. So if I asked you to design a circuit that checks if a number is, checks if 2 numbers sum to 5, this would be the solution, assuming that we had access to this black box. So let's try to implement this circuit right now, of like it takes in a 9-bit value and then checks if that value is equal to 5. Let's go and spend a minute thinking about this, see if you can implement this circuit using like a logic expression. You don't actually have to draw out like full like NAND gates and NOT gates and everything. Just write it out as just an expression. Okay, yeah, spend 1 minute thinking about how to implement this. So I'll write it out a little bit clearer. So if we have the bus like S, maybe for sum. So S from what's the bit width? Or what are what's the bit range that I would put in these brackets right here to specify that it's a 9-bit number? What is it? 8 to 0, yeah. Right. 8 to 0, okay. So this is a 9-bit value, okay. And we want to check if this is equal to 5. Okay, yeah, so what do we do? Yeah.
I guess start with a bitwise
XAND?
XAND.
XOR? There is no XAND, but there's an XOR. Yes.
Well, would you do like a bitwise AND with each of like the bits of the number 5 and then the input?
That's close. Sure. Yeah. So let's keep thinking about it. Any other ideas? Yeah. Yeah.
You do a bitwise XOR and then not,
Mm-hmm.
and that would get you 1 for each digit that's the same, or each bit that's the same.
Sure. Yeah. That's interesting. So XOR, if we have an XOR gate, right? Usually, like we could say that this is equivalent to like the not equals to operator, because like if we pass in like whatever 1 and 0, then this will say, oh yes, these are not equal to each other, so therefore we get a 1. Versus like if we had like 0 and 1. Oops. If we had 1 and 1, then now we would say these are equal to each other. So they're not equal to each other. They're not equal to each other. So it's a 0. Yeah. Cool. So okay, but potentially we could make like an equals to operator if we now just what do we do? What can we do to make this an equals to operator?
Not gauge?
Yeah, like a NOT gate. And we probably just put like a little circle right there. Sure. So okay. Yeah. Kind of cool. So we could potentially do this now for, oh my gosh. Oh, this sucks. Sorry. Notability, I swear, I'm gonna fight the people. They added a new update where when you erase something, it changes your tool automatically to the last thing you used. And oh my gosh. Okay. I don't know if I can change that in 5 seconds, but this is the worst app ever. It used to be so good. Handwriting? Anyone see it? Palm detection? Auto detect eraser?
Yeah,
Deselect. Thank you. This is awesome. Okay. Thank you for your help. Anyways, okay, cool. What was I talking about? Oh yeah, so okay, so we have now S8 to 0, and we have this we have this equals to operator. So we have that the XNOR operations, that's what the name of this symbol is XNOR. This is the same thing as equals. Yeah, so now we can just take every single bit of this S8 to 0 and we can XNOR it with every single bit in the number 5. Or if you wanted to make an equals to like 7 operator, then we would XNOR it with every bit in number 7. Okay, so let's just, I don't know, quickly do that. So, so if we have 9 whole bits, so 1, 2, so this is like S8 all the way to S0. If we XNOR it, and I'll just make this square be an XNOR. Okay. So if we want it to equal 5, what should we feed in as like the second input to each of these XNORs? Right. So this is feeding in like S1, this is S2, this is S3, and then all the way up to S8. So what goes right here for the second input of S0? Yeah, 1, okay. And then, okay. And then for S1, what is the second input? 0. And then what is the next input? 1. What is the next input? 0. And then it continues all the way until S equals 8, where everything in here is equal to 0. And the reason for this is because this is how you represent 5 in binary. Right? We have 1, 0, 1. That's 5 in binary. Yeah. So you can just feed in any number that you want right here. And that will be like your equals to thing. Cool. Okay. Is that the only way to implement this? There's actually a little bit more efficient way of doing this. Yeah.
You could just manually check to make the right one, like instead of like and gates.
Right. Yeah. Yeah. So we could have AND gates, but now, so I'll show you this. So if you have, yeah, if we're trying to check if it's equal to 5, then if we have, yeah, so 5 is 1, 0, 1, so we could just, sorry. Wait. Yeah, so you take one single big AND gate and feeds in all like 9 inputs. But for every time that we expect a 0, we actually want to like invert that input. Yeah. So now this would be, sorry, I guess we would want to have a bunch of inverters all right here too. Yeah. So right here, if we passed in the number 4, right? So number 4, so these are all zeros. Okay, awesome. Except right here, we have a 1, and then a 0 and 0. So in this case, all of these would evaluate to true because we're passing 0 into all these NOT gates, and then we have this 1 passed into no NOT gate, and then we have the 0 passed into the NOT gate. But then this final bit right here, this is passing a 0 into the AND gate, so it will eliminate everything. But now if we inputted 5, then now every single input to this AND gate is set to 1. Yeah. So this is actually a little bit more efficient way of implementing like an equals to a constant. Yeah. Okay, very cool. Makes sense? Good. Okay. So now we have access to this equals 5 black box. We can either implement it with XOR gates, XNOR gates, or we can implement it using like a really big AND gate. Okay. Okay, keep this in the back of your mind. I'm going to move on to something completely different, and we'll come back to this equals operator that we just made. Any questions on this?
Can we go back?
Okay. Yeah. Up to here?
Yeah, I just want to see the previous.
Yeah, sure. Uh-huh. Okay, excellent. Okay. We're going to cover a brand new logic cell. This is called a multiplexer, and it looks like this. Multiplexer, also known as a mux. Okay. And the way that this works is you will have two inputs on the large end of this trapezoid, and they will be marked with a number on them. So they may be marked with 0 and 1. And then on the top, you have an address bit or a select bit. So I'll call this S. And when S equals to one of the numbers, then that input is passed to this output over here. So if S equals 0, then whatever data is right here, so if this is input like A, if S is 0, then the output will be directly tied to A. So I'll say S equals 0, versus if S equals 1, then we will take this bottom one here, and maybe I'll call this B. Yeah. All right. Cool. This is a very powerful sort of circuit right here because it's very readable. It's like you look at it and you're like, oh, okay, yeah. So what are we currently selecting right now? Are we selecting A or are we selecting B? Yeah. Let's create an inverter circuit using a mux now. Take a second, actually. Go and see if you can do this on your own. Go and create an inverter circuit using a mux. Sure. Yeah. Thanks. All right. Do we have a thought? Any ideas? Yeah.
So, like, if A is selected and S is 0,
Uh-huh.
then you put A 1.
Sure. Yeah.
And then if B is selected when S is 1, then you put B.
Yeah, I really like that. So I'm going to draw another circuit down here. So I'll call this inverter. Yeah, cool. So we have a mux. And so yeah, if select is equal to 0, then we will take this path. And in this case, we want the output to be 1. So we just hardwire a 1 in there. And if S is equal to 1 now, then we want the output to be 0. So now we have implemented an inverter using a mux. And actually, you can use a mux. You can use muxes to implement any circuit that you want. You can build anything you want just out of muxes. You actually don't need any more AND gates or gates. And actually, I would kind of encourage you to only use muxes from now on. So maybe start thinking about, yeah, how would you do things in muxes? Generally, it's more human readable to use muxes in your circuit diagrams. Do you have a question? Yeah.
Yeah, so in this example, you use
Huh?
S like the input.
Exactly. Thank you. I'm going to write that out. Actually, maybe I'll rename this to A. Yeah. Sure. Okay. Yeah. Another question.
All the local tables on
on the FPGA because we're using muxes?
FPGAs actually come with a bunch of muxes that you are able to use. So FPGAs are built with LUTs and muxes. Yeah. And that's like their main logic cells. And then there's a couple others, but like those are the main ones, yeah. Although you can implement muxes using lookup tables, you can also implement lookup tables using muxes. But yeah, there are mux cells and there are lookup table cells.
Do you know how the lookup tables are implemented though? Like on hardware?
They are they use like a ROM like circuit, like kind of advanced analog thing that I don't know off the top of my head. But yeah, they use like a more advanced like analog thing. Yeah. Yeah. The question?
So is a lookup table basically just a box with like lots of inputs?
Exactly. Yeah, that's a good way to think about it. So, notice, so with this inverter right here, we are feeding in constants, but we can actually feed in anything we want. So maybe another thing we can do is maybe we want like an enable signal. Okay, so we can say right here, enable. So whenever the enable is set to 1, and I'll reverse the numbers here because it's totally fine to do that. So if I set that enable as 1, then maybe I want to have the input A be set to the output. But maybe if I'm disabling this circuit, so I set whatever, enable to 0, what would you imagine, I don't know, would probably mean by like disabling? What should we put here? Sure, yeah, I don't know, we could just put 0. Okay. Yeah, so we've like disabled A. Does this remind you of anything, this circuit right here?
Switch.
Yeah. An AND gate, yeah, this is actually just an AND gate, right? This is just A and enable. Yeah. Yeah?
So would a mux inverter only have one input?
Say it again?
Would a mux inverter only have one input?
Mux inverter.
The inverter you built.
Correct, yes, because these are hardwired inputs right here. Yeah, and this AND gate has has 2 inputs now, A and enable, and then this mux input is set to 0. Yeah. So actually, kind of an interesting thing. Anytime your tool sees, like your Verilog tool, sees that you have designed this mux structure right here, it will actually optimize it into an AND gate for you. So it won't create like a full mux cell, instead it'll just create an AND gate. Similarly with this right here, if it sees that you ever create this, it will actually simplify this into an inverter. Yeah. And you can make any gate that you'd like using a mux. Yeah, like I said, so you can do whatever you want with a mux. Okay. I now want to talk about a very kind of standard problem that you'll have to do that is solved using muxes. So let me remember the wording of it. Yeah, okay. So if you have now 4 inputs, so maybe we have D0, D1, D2, and D3. Okay. And maybe we have an address to select which one of these we want currently to be outputted. Is that right? Yeah, yeah. Okay. So let's assume we can only use just the standard kind of 2 input muxes that we have right here. Okay. So if we have now a select, so how wide should our select be in order to be able to access each one of these inputs? Yeah, it's 2 bits, right? So if we have 0, 0, that's the first one. If we have like 1, 1, that's the last one. Yeah, okay. So how would we implement this now using, using 2 input muxes? So we have a single output right here, and we want to assign the inputs to the output, depending on what select is. So go and take a second, think about this, and work with the person next to you. We'll come back in a minute. All right. You know, there's actually a few ways you can do this. Anyone figure out a way? Yeah? No? Yeah? Yeah.
So you start with having like D0, D1,
Okay.
Same with,
Which? Oh, sure.
or yeah, same with D2 and D3.
Okay.
And then you have one of the selector bits go into both of them, presumably. I think it would be,
Mm.
you'd have the least significant go into both, or I think you could do it either way, but.
Sure. So you're saying like select one or something
Yeah.
goes into that, right? And then we have maybe another mux to now choose between these two.
Yeah.
Sure. Okay. Let's see what happens when we do it like that. There we go. Yeah, was anyone else kind of thinking of this structure? Yeah. Let's go and just kind of see what happens. So if we have S0 now, okay. Let's say we wanted to select D3. What should S be? 1, 1. Okay. So in this case, so we, if both of these are going to be 1, then where should I put the 1 here in order to choose D3? Yeah, on the bottom, right? So if S1 equals 1, then choose D3. Okay, yeah. And then similarly, up here, so if S0 is 1, then where should I put the 1 on this? Yeah, on the bottom. Okay. Cool. Yeah. So now, okay, looks like 3 works. Okay, now let's try, I don't know, try 0, 0. So 0, 0 should probably select this guy. So, okay, what should happen? So if S1 equals 0, where should I put the 0? Yeah, on the top. Okay. And then, is it okay? Did we reach a contradiction here? Is if S0 is 0, then where should I put the 0? On the top. Okay, so it looks like we didn't have a contradiction. So yeah, in theory, so maybe we just have like this structure right here, right? And maybe let's try one more. So if we have 1, so I guess like 0, 1, right? So 0, 1, so if S1 is, what would S1 be if we were feeding in the value like 0, 1? S0. Yeah, so S0 would be 0. Okay. So now we take this path, it looks like, right? We take D0 and then because we wanted D1. Okay. All right. How do we change this to correct this? See the issue? Yeah, so it currently does not work when S equals 1. Okay, what do we do? Yeah.
You just swap the S1s with the S0.
Yeah, that's what I'm thinking, right? Because we were using this S1 to choose between these two, but S1 is actually, it's a higher order address. So it should actually probably be selecting between like these two muxes, because those are like a higher order level. So, okay, so instead of S1 and S0, then maybe let's try S0 and S1. Okay, so now let's test that. So if we have the value 1, then now S0 will equal 1, so it'll take D1, good. It'll feed in here. Now we have S1 equals 0, so then we will take this and swap. Cool. Okay, so it looks like it works for now 0, 3, 1. It also works for 2 as well. We can see that when S1 is 0, D2 is grabbed, but then now we check S1, which is now 1. So yeah, for S equals 2, D2 also works. Okay, makes sense. Cool. Okay, there's a few ways, but we could do it. This is actually the most efficient structure of solving this problem. We have another question.
Isn't it when we say 2, we want 2, isn't S1 1? So then 2 is 1, 0. So S1 will be 1.
Oh, you know what? You are completely right. My mistake. I meant to change this also to 0. Yeah.
Okay.
Yeah. Thank you. Thank you. Question.
What logic expression does this equal to? Like, what does it do?
So we can talk about the actual expression in a second. But what this effectively does is it just routes out the one of these 4 inputs to this output right here, depending on what the select is. So this is a 2-input select. So actually what we've just designed right here is actually, we would call this a 4-input mux. Yeah, look at this. And the symbol for that, and I'll keep it on the same page. The symbol for that is exactly the same as a 2-input mux, except now you have 4 inputs. So D0, D1, D2, D3, Y, and S. Okay. And the way that we write like 4-input mux is we would call this a mux 4. So this is a mux 4. Yeah. Very good. Okay. But going back to just like a mux 2. Well, I mean, how would we implement like a mux 2 in general? Like, so remember, so it has three inputs by default. Like we have S, A, and B. So we could probably like implement these using like logic gates, right? It's just a 3-input circuit, produces 1 output. So we could make like a truth table, kind of go through that. Yeah, keep that thought. We're going to go over the implementation of a mux in a second. First, let's do another kind of practice question. So here's how you make a mux 4. Now we're going to kind of go backwards now, and we're going to say that assume we have 4 outputs. So assume we have D0, D1, D2, D3, and we have 1 input, A, or 2 inputs, because then we also have S for the select. And what we want is for all of these to default to 0, okay? But if S equals the address, then instead it should equal A. So an example, so if S equals 0, then D0 should equal A. So if S equals 0, then D0 should equal A. If S is 2, then D2 should equal A. So yeah, okay. Go and think about how to do this now using 2-input muxes. Okay, so the first thing that I look at is, so we're going to have 2 possible outputs for each one of these outputs. Either it's going to be 0 or it's going to be A. So what that makes me think is, well, maybe we can have a mux where we have 2 inputs, and 2 inputs are 0 and A. Okay, so we have mux, we have A and 0, okay, and let's just copy this down now. Oops, come on, no. There we go, okay. Okay, but if we do this, then what is the final input that we're missing? Or what are we missing from these muxes? Yeah, we're missing the selector. Okay. Well, can we just hook up like this S directly to these? I don't think so. Yeah. Okay. So what do we do? Well, remember, so if S equals 0, then for in this case, we want to take A on this one. If S equals 1, then instead we want to set this mux. Is there a logic cell that we spoke about earlier in this class that could help us? What is it? What was the first logic cell that we spoke about for the first like 10 minutes? Equals, right? So maybe what we can have is just a little thing right here that's just equals 0. Yeah? And then maybe one right here that would, what would this cell be? Yeah, equals 1. Okay. Another one right here, what would this be? Equals 2. And then finally, what's the last one? Equals 3. Sure. Yeah. Okay. And then each of these are all going to be fed by S. Okay. Sure. Lots of great applications for muxes. You can basically put them wherever you want. If you ever feel like it will improve the readability of your schematic, then I would just throw one in. You can pull out like an OR gate or AND gate or whatever, just make it a mux. Now we're going to show you how to do this in Verilog. So we're going to do this exact problem now, where we have 4 outputs and we have 2 inputs. We have the select and then we have the data to pass through. And we're going to implement this. Okay. So if you remember, so this is Digital.js Online. This is a website that you type in Verilog on the left side, and then you hit run, and it will create a schematic on the right side. So this is going to be very helpful for us. So we have, data out, or data 0, data 1, data 2, data 3. Okay. The way that you create a mux in Verilog is with the conditional operator that is found in basically every C-like language. And so first we do assign, and let's do D0. So we say D out 0 is equal to, and so it is of the format condition. So I'll just write this out. Condition, question mark, and if the condition is set, then this is the 1 case, and then colon, then this is the 2 case. Okay. So this is how you create a mux. So now for D out 0, what should our condition be? Yeah.
If it's equal to 0?
Yeah, specifically which one? Yeah, address. So if address equals 0, oh, look at this, equals. That's cool, right? We did that already. So this will automatically create an equals to 0 cell for us. And then what is the case when, oh, sorry, I meant to say 0 case. My mistake. So if this is set, then what should we put here? So if address is 0, so it is going to be D in. Yeah, cool. Okay, D in. And what is the case if it's not equal to 0?
0.
Yeah, it should be 0. Okay. Great. So let's now copy this down. So now 1, 2, 3. 1, 2, 3. Yeah? Makes sense? Okay. So now we should have a bunch of these muxes. We might have some optimizations done for us. It might try to eliminate some of the muxes, so we'll just see what happens. I actually didn't test this, but hopefully this works. Okay. Oh, this is perfect. Yeah, awesome. So here we can see we have 4 muxes. In each of these 4 muxes, you can see which line of the Verilog it actually represents. Yeah. And then we have this equals 2, this equals 1. Then we have this NOR gate. What does this NOR gate mean? Yeah, it's equals 0, because remember, so when you have a NOR gate, it will only output 1 if every single input is 0. Yeah. So this is the same thing as an equals 0. Then yeah, it equals 3. So there we go. So this is our entire circuit implemented in Verilog. Here we go. Yeah. Cool. So I have something to note. So I have right here, I have this parameter specified called data width, and it equals 32. And then right here, I'm specifying like logic data width minus 1. So this is actually creating a parameterized module where I can come in and I can say, you know what, actually I want this now to be 8. So now all of my data widths, like all of my buses, will now be size 8. So if I hit run, then now we can see on the schematic that, that now the outputs got a little bit shorter, and yeah, you can see these buses now have a number 8 over them instead of a number 32. Okay, so these are parameters. Occasionally you will see them in the labs. I have some issues with them, and I can talk about them with you if you'd like to know my issues with parameters. But yeah, cool. Okay, makes sense. Good. Yeah.
So case 1 is where the condition is true.
Exactly. Yeah. It's the condition. It's when the condition equals 1. Yeah. Exactly. So I could call it like true case as well, and false case. Okay. We are going to do a quick Canvas quiz. I've not yet created the submission box for us, so let me create it super quick. The question that you must all solve is to create an inverter using a mux in Verilog. Do we have an answer? So if I call this mux, okay. Okay, let's, oh yeah. Okay, just a second. So, okay, maybe take a break from it in a second, for a second, because we'll just go over what the answer is anyway, so you can fill it in a bit. But I'm going to walk through the construction of a module from scratch, because you will need this for your lab. What you will have to do in your lab is start with, I think you're given one single starter file, and you have to create a bunch of other modules from scratch. So when you create a module, so that this first step is you create a file, and the file name should exactly match whatever you want your module to be called. So if you wanted it to be called like inverter or something, then you would want to name your file inverter. In this case, it is called mux, so let's call it mux. But first we type in the word module, then mux. Then we add parentheses, and inside the parentheses, we specify our ports. So if we wanted to create an inverter circuit, what would our ports be for this? Yeah.
Like 0 and 1?
So for an inverter, what is like the inputs and outputs for just like an inverter? Yeah.
In and then out.
Yeah, just like one input, one output, sure. What should we call our input? Sure, yeah, let's call it A. And it's also important to specify the data type. So I'm going to call it logic. Logic is just the most generic data type. I won't go into the different types in this class, but just know there are multiple. So that's why you need to specify logic. And then let's specify an output. Okay, and what should we call our output probably?
Out.
Yeah, sure, okay, out, okay. Slight, okay, adding a rule in you, starting from now on. From now on, every single module port should be given an underscore and then an identifier of whether it is an input or output. And so the syntax would be underscore I for inputs and underscore O for outputs. This is the standard across basically every single person who writes Verilog. If you go on like large CPUs that are implemented, if you go on GitHub, yeah, look at like the 10,000 line projects that all utilize Verilog. All of them have underscore I, underscore O to denote inputs and outputs. It just ends up helping a ton later on. So okay, so good. So this is new best practice that we've all learned. Underscore I, underscore O. You will be graded on whether or not you have underscore I and underscore O in all of your labs. If you do not have that, you will lose points. Okay. And then after you've declared all of your ports, then you type in end module. And this denotes that everything inside of like this region right here is going to be the contents of your module. So okay, now, can you all tell me, maybe just say it in unison, how do I implement an inverter using a mux? Okay, what's the first thing I type? Assign what? Out underscore O. Now what? Equals, yeah, we just shouted out equals. What is it? Yeah, sure, A of I, okay. And then what's after that? Question mark, okay. What is the true case for this? 0, sure, okay. And then what's next? Colon, yep, and what's next? 1, okay. What's next? Semicolon, good, okay. Yeah, let's hit run, see what happens. Cool, so there's our mux. And so right now it's outputting 1, even though A is 0. Then when I change A to 1, then now it outputs 0. So this is now an inverter. Kind of quickly, I'm thinking that Yosis actually has a built-in optimization to turn this into an inverter. Let's double check. Yeah, so cool. So there's this checkbox right here, optimize in Yosis. Yosis is the synthesis tool that that this tool happens to use, that this website happens to use, and I guess it has, Yosis inside of it has ways to convert known mux uses into more reduced gates. So yeah, for example, this inverter right here. So yeah, kind of cool. Okay. If you haven't finished the quiz, this is the answer. So type that in. Yeah, question?
Wait, so again, so 0 is
So the first thing, the one that comes right after the question mark, is the true case, and the one that comes after the semicolon, or after the colon, is the false case. So in this case, the true case, we want it to be 0 because we want it to like invert this A1 or AI. Question?
Are the participation quizzes marked by whether or not you got it right, or just by participation?
It is just participation, yes, but it is helpful for yourself to remember what the answer is so that you can go back and review it later. Yes?
Would it matter if the conditional was set as equals 1?
Oh, sure. So if you say equals 1, it is the exact same thing. Yeah. You could also say is like not equal to 0. Yeah. But note, how wide is this AI right here? How wide is this? It's just one single bit. If we wanted multiple bits, then we would have to specify like a bus here. Then you would kind of have to, be more mindful with your equals 0, equals 1, whatnot. Okay, good, makes sense. I want to quickly pull up your lab now. So here's your lab. So I'll go through this really quick. So you are making an ALU, an arithmetic logic unit. In general, it is useful for chips to have an ALU on them because most likely you have a lot of data that's being fed in, and it's nice to kind of just funnel all of that data through one single channel that does all of your computation. Or maybe you channel now all your data through some other thing that deals with all of your like load store methods. So having an ALU is just very helpful. So an arithmetic logic unit is a unit that deals with all of your arithmetic that you need on your chip. And in this lab, we are assuming that our chip that we have this ALU on. For some reason, the only things that it needs is addition, subtraction, floor of the log base 2, and square root. So you will be creating an ALU that can perform each one of these operations. But notice that depending on this operation input right here, operation, you will have to, if operation equals a certain selector pattern, that's when you want to use the specific operation. So go and read through this. This is your lab for this week. It is due this Thursday, so please come into lab as much as you can this week to try to finish this early, because it might be a little bit more tricky than last lab. I want to show you one more really cool thing. So I saw a couple people do this, but not too many. So when you run make sim, what does sim mean? Yeah, simulations. Okay, so when you run the simulations, it does a bunch of tests, make sure that it works. Looks like it's all working. But then in the README, there was something else after this. There was gtkWave dump.fst. Did anyone run that? Yeah. Did we see what came up when we ran that? Like this window, right? Yeah. Well, if you expand this out, and maybe we go through each of the modules. Okay, so we have our ALU. Well, what happens is I can open each of these wires right here. And what we have is a graph, just basically like an oscilloscope layout thing, where we have each of our different wires, and they're all represented as buses. So we can zoom in, and we can see that they're all displayed in hex. But I can change them to be now decimal, and I can change this to decimal that's just right-clicking on the name. And so it looks like, so this operation 1, I think this is supposed to be addition. So for example, like 27 plus, oops, there we go, okay. So like right here, 27 plus 71 is equal to 98. It's a very small font, but hopefully you can still kind of see that. What you may have are bugs in your code. So now when you open up gtkWave, you can go through and see like exactly why you're getting certain bugs. You can look at this. The simulation will stop running as soon as it finds a bug, meaning where should I go to in this simulation if I want to find where my bug is, if it stops running the simulation when it finds a bug? I should go to the very end. Yeah. So if I go to the very end, in this case, the simulation worked, it all passed. But in general, if you get errors and you're like, oh no, I don't know where the error is, like this is so long, there's so many things switching, it actually means that everything was working. It was all working, boom, until the very end. Then you notice, oh, okay, maybe the operation now changed to floor of the log base 2. So now I know, okay, so the issue is probably in the floor of log base 2. Or it's when I get overflow or something. Yeah, question?
I saw that you pushed the lab to grade scope, but I'm not seeing it on Canvas.
Oh, it should be on Canvas. I think people were starting it. I didn't post. There's still some things missing, but I at least posted the starter files. Yeah.
Oh, is it in the files?
No, it's not in the it's in the module. Modules. Yeah. Any other questions? Yeah. Actually, we have a quick announcement. Please be quiet. Jacob is going to give a quick announcement about tutoring.
Quick announcement, if you guys are in tutoring today, I'm going to walk over to Oaks and we can all walk together. If you could sign up when you want to come, you can also drop in. But if you sign up, it lets me know how many worksheets to print out and all that stuff. So, yeah.
Great, yeah, please go to that. It sounds like a great learning resource. All right, thank you, everyone.